Okay, hello again. Folks, this is the video accompanying the lessons you can see on the screen just now. So that is Year 9 Core Chemistry, Week 5, the second lesson of Week 5. So that's the last week. So actually this is the last video for Year 9 Core. For Year 9 Triple, it is the second lesson of Week 4, so the week commencing the 29th of June. It's your second lesson, chemistry lesson of that week. And for Year 10 Core, it is Week 5, so the week commencing the 6th of June. It's the first chemistry lesson of that week for the Year 10 Core group. Hope you're all safe and well, and we'll crack on. So, 5 quick questions then. You have got 5 questions or tasks to do on the screen. Just pause that and have a go at those, and we'll go through it. Okay, hopefully you've had a go at those. So, first one, state the 3 types of bonding. Well, we know from previous videos the 3 types of bonding are ionic bonding, covalent bonding, and the one we're going to look at today. So you may or may not have got that one. For number 2, the 2 giant covalent structures, well, that was in the last video that we covered. The 2 that we covered were diamond and graphite. You could have also had silicon oxide, which we mentioned briefly. Number 3, why can graphite conduct electricity? So there's a slide with the answers here. Because it has spare or delocalized electrons moving throughout the layers, which can carry electrical charge. Number 4, in diamond, how many other carbon atoms is each carbon atom bonded to? Bonded to 4 other carbon atoms. And number 5, what does graphite have in its structure that make it softer than diamond? And the answer to that is it has layers. The carbon atoms in each layer are bonded very strongly together, but the layers themselves only have weak forces between them. So when you apply a force to the layers, they slide off. Which is why we can use graphite in things like pencils and lubricants and so on. Okay, moving on to what we're looking at today, which is the 3rd type of bonding, which is metallic bonding. So we're going to look a little bit at the structure of metals, why they have some of the properties they have, and how the bonding within metals works. Because we've looked at ionic bonding, which is metal to non-metal. We've looked at covalent bonding, which is non-metal to non-metal. We're now going to look at how the forces involved in holding metal structures together. So we know metals, we should know that metals have high melting and boiling points, and metals, generally speaking, are hard and strong. They have many other properties, but those are some of the key ones. And it is the bonding within metals that allows them to have these properties. Metals have regular structures. They have regular lattice structures, which means they're made of repeating units. So they're not just random collections of atoms. They are formed in repeating regular structures that we call lattices, and they are held together by strong bonds, as you would expect, which is why metals are hard and why they are strong. Okay, so how this works is metal atoms are trying to achieve or gain stability. The way that they can do that is by having a full outer shell. Now when we looked at ionic bonding, we looked at the fact that most metals do not have full outer shells. They have 3 electrons in their outer shells, but they generally have 1, 2 or 3 electrons in their outer shells. So to achieve a full outer shell, what they do is they lose those electrons, and that leaves them with a full outer shell. So the electrons from the outer shells within a metallic structure, what happens is the metal atoms lose their outer shell electrons, and they form positive ions. So the electrons then are loose, as it were, or delocalized or free within the structure of the metal. And they form what we call the sea of negative charge, or a sea of delocalized electrons, which flow around the positive metal ions. Because the metal atoms lose their outer shell electrons into the structure, they become positive ions, and then you have the negative electrons moving through the structure around these positive ions. Okay? Now, we know opposites attract, so the positive metal ions are attracted to the negatively charged electrons that are flowing through the structure, and that is what holds the whole structure together. That is called an electrostatic attraction. Positive attracted to negative is called an electrostatic attraction. So what you have is the positive metal ions, which have lost their outer shell electrons, and the outer shell electrons that they've lost are just flowing and moving through the structure, and the whole structure is held together by the attraction between the negatively charged electrons and the positively charged ions. And these negatively charged electrons are called delocalized electrons or free electrons. Okay, and the key point there is the electrostatic attraction between the negative electrons and the positive ions that hold the whole structure together. That's a very strong attraction. That is why metals are hard and strong. It is also why they have very high melting and boiling points, because it takes a lot of energy to break that attraction and split the metal up into its smaller particles, to melt it or to boil it indeed. Okay. So, we've spoken about the fact that metals form a regular lattice structure with these electrons moving throughout the positive ions in that structure. Because they're free to move, that's why the metal can conduct electricity. We'll get to that in a moment. And also because they are negatively charged, they're attracted to the positive ions, and that holds the whole structure together. That is metallic bonding, the attraction between the negative electrons and the positive metal ions. Now, as we've said, metals have very high melting and boiling points. Gold, for example, you have to heat that to 1064 degrees to melt it, and almost 3000 degrees to boil it. That is because the attraction between the negative electrons and the positive metal ions in the structure of the metal is so strong. It takes that much energy, that much heat energy, to break those attractions between the ions and the electrons, and to break the structure down and cause it to change state. Okay, so that's why they have high melting and boiling points. Why they conduct heat and electricity is because of the delocalized electrons. Because they have these delocalized electrons in their structure, those delocalized electrons can carry heat energy through the structure and transfer it throughout the structure. They can also carry electrical charge through the structure and transfer that throughout the structure. That's why metals are very, very good conductors of heat and very, very good conductors of electrical energy. Okay, because of the free or delocalized electrons in their structure, which can transfer heat energy and they can carry electrical charge. Okay, you need to be clear on that as well. It is the delocalized electrons in the structure that allows the metal to conduct heat energy and electrical charge. Okay? So these are very key points if you're asked about why metals can conduct heat and why metals can conduct electricity. Now, because they have a regular structure of layers within a metal, metals are what we call malleable. Okay? Because the layers can slide over each other. Not quite as easily as graphite, so they don't slide off each other, and they don't slide as easily as graphite, but they do slide. If you apply force to a metal, it will bend rather than break it. If you have a metal bar and you apply a force to it, it will bend and change shape. If you have a piece of glass in the shape of a bar, or a piece of plastic in the shape of a bar, and you apply force to it, it may bend a little bit, but when you release that force, it will go back to how it was. Or if you increase that force, eventually it will just break or snap. Metals don't break or snap, and they don't go back to their original shape. They are what we call malleable. They can be bent into different shapes or hammered into different shapes by applying a force to them. Because what happens is the layers slide over each other and the whole structure changes shape. Okay. That's why they're not brittle, and that's why they're strong, because they're able to change shape when a force is applied. So they don't break easily. They are malleable and they change shape. Okay? It also keeps its shape because as the shape changes, the electrons move through the structure and that maintains the attraction between the negatively charged electrons and the positive metal ions. So even though it has all changed shape, the bond, the attraction between these ions and these electrons is still just as strong. So it is just as strong as in its new shape as it was previously. All that's happened is the layers have shifted. You can even pull a metal into a wire. We say they are ductile, they can be drawn into wires, you can do that, and it will still maintain a strong structure even though it has been pulled long and thin, because you still have the electrons in the structure attracted to the positive ions, and you still have those strong attractions holding those together. Okay, now, the last one on the fact book talks about alloys and why alloys are harder than pure metals. Well, this comes back to this idea of layers again. If you apply a force, as you can see on the screen now, you apply a force to a pure metal, all the atoms in that pure metal are the same. So the layers slide over each other very easily. Now that actually means, even though we don't think about metals as being soft, pure metals, relatively speaking, compared to the metals that we actually use, are quite soft. We don't use pure metals for very many things, other than to make what we call alloys. Okay, alloys are metals that have been mixed or joined with other substances to give them different properties. One of those properties is alloys are harder than pure metals, because as shown on the little animation, when you apply a force to a pure metal, the layers can slide very easily because the atoms are all the same size, so the layers move easily. If we look at an alloy, where you may have different substances within that structure, all of a sudden you've got different size particles, because you might have two elements mixed together. That means the layers will not slide over each other so easily. So if you all of a sudden have different sized atoms within this structure, to make an alloy, if you mix it with a different element, those different sized atoms will stop the layers sliding so easily. That means the layers lock, and therefore the alloy can take more force before it changes shape than the pure metal. That's why we tend to use alloys for things rather than pure metals. Pure metals are very useful because we can use them to make alloys, but in terms of practical uses we would use alloys. One of the reasons would be because alloys are harder, because they have different sized particles, different sized atoms in their structure, and that stops the layers from sliding over them so easily. They still have free electrons moving through the structure, so alloys will still conduct electricity and heat very well, but they are harder or stronger than pure metals because the layers won't slide so easily. Okay, so there's the key facts we were covering. Metals are giant structures of atoms arranged in a regular lattice pattern. Electrons in the outer shells of metal atoms delocalize and therefore are free to move through the structure. It is the electrostatic forces between the metal ions, the positive metal ions, and the delocalized electrons which causes the very strong attractions within the structure, and that's why metals are hard and strong and have high melting and boiling points. The delocalized electrons can move through the structure and they can carry electrical charge and they can carry heat energy, which is why metals are good at conducting heat and electricity. And the last point we looked at was the fact that alloys are more useful in some ways than pure metals, because pure metals are malleable, because the layers within their structure can slide over each other without coming apart. But in an alloy, because you have different elements in there, you have different atoms or different particles within the layers, that stops them from sliding over each other so easily, which makes the whole structure harder and stronger. Okay, hopefully that has made sense. Thank you.